Hi, you guys. So I'm going to finish up the 2.8 notes. And by finish up, I mean just do the entire section. So as we all know by now from class, it really did take the whole class to walk through nice and slowly how to build this unit circle. So you are going to need this out. And on your version, that yellow paper, there's one on the back. I'm hoping that you guys take advantage of that to use that space to practice this, since now that you know you will be needing to replicate the unit circle on your own without any resources. So this is about as far as we got with the notes in class after building that unit circle. So we know the unit circle is centered at 0, 0 with a radius of 1, which is why it's called the unit circle. We've established that the unit circle all the way around is 360 degrees or 2 pi radians. And now we're going to move on in through this notes packet. So the image of x, y under a rotation of magnitude theta. In other words, it's just saying if you rotate xy around the unit circle, the notation to represent that is capital R with a subscript theta of xy. That just means rotate this point this many radians or degrees. Cosine and sine are the first and second coordinates of the rotation 0, 1. And we covered this in class. And I'll just quickly demonstrate why that's the case. So let's say I have this angle measure theta on the unit circle. This xy coordinate, if this is the x and y value, remember this length down here of x and this height of y, in terms of sine and cosine of theta, if this is theta, and on the unit circle, this hypotenuse is 1, as we talked about in class. Cosine of theta adjacent over hypotenuse is just x over 1. So cosine of theta is literally the x value of this triangle formed by this rotation. So, and then we saw the same thing with the sine of theta. So the sine of theta is opposite y over hypotenuse, which is y itself. So every ordered pair around this unit circle is an xy coordinate that is the cosine of the rotation, comma, sine of that angle measure. So that's what this is. This is just what that notation is saying. So when I rotate 1, 0, any rotation around the unit circle, the new coordinates are the cosine of that angle, comma, the sine of that angle. And then tangent of theta, let's see what tangent of theta equals. Opposite over adjacent is tangent, right? So Katoa, so opposite y over x adjacent, y divided by x. Let's think about that in terms of sine and cosine. That would be y divided by x, that's sine over cosine. Tangent of theta is literally the ratio of the sine of theta divided by the cosine of theta, and that's going to be super useful to us. So if you didn't know that already, that's one that you're going to be using a lot, because if I know the sine and cosine of an angle measure, then I can very quickly compute the tangent by taking that ratio. All right, so moving on, complete the unit circle by filling in the names of the angles. So I am not going to complete the unit circle on the video notes. I encourage you to pause and build this yourself. It consists of knowing how to do two things. The first thing would be labeling the inside of the circle with all of the radian measures of each of these lines which are marking the rotation. So in other words, this is 0 radians, this is pi radians, all the way around 2 pi radians. So I'll put that there as well. If this is pi halves, and so on and so forth. So you should be able to do that. And then you should be able to label all of the ordered pairs around it. So our 5 key points are the easiest: over 1, up 0, over 0, up 1, -1, 0, 0, -1. And then all these others, as you hopefully remember from class, it relies on our knowledge of those special right triangles. And we will move away from those special right triangles. You do not need those every time you fill in this unit circle. So some of it will come down to just memorization, but we can always build it with special right triangles if we need to. So I'm going to pause here, fill mine in so that we can reference it, and I hope you choose to do the same. All right, so I've got my unit circle all filled in here with the radian measures around the inside, and then each of the ordered pairs that corresponds with the rotation of that radian measure. So revisiting this notation, which means rotate the point 10 3 pi fourth radians. So 3 pi over 4, here's 10, here's 3 pi over 4. So if I rotate this 3 pi over 4, the image of 10 is now negative root 2 over 2 comma root 2 over 2. In other words, the cosine is negative root 2 over 2, and the sine of 3 pi over 4 is positive root 2 over 2. So negative root 2 over 2 comma root 2 over 2. So we're just rotating our point however far. Now, negative rotations is something that may throw you off a little bit, but it is it should click here pretty quickly. So negative 7 pi over 6. Let's look at the rotation for positive 7 pi over 6. So if we look here, we see 7 pi over 6 right here. So follow that rotation. If I'm starting here, going all the way around the unit circle to positive 7 pi over 6. Now, I just visualize it. I'm 30 degrees or pi over 6 past the halfway point. So when I rotate negative 7 pi over 6, that means instead of starting in this counterclockwise rotation, I'm actually going to start from 0 going the opposite direction. But I need to go negative 7 pi over 6. So I'm going negative in the negative direction. I'm not stopping at 7 pi over 6. I'm stopping at negative pi over 6, which would actually be the same as 5 pi over 6. So I start in that negative direction, past the halfway point, and go 30 degrees farther, just like I went in the positive direction here. So negative 7 pi over 6, a rotation of that is actually the same as the rotation of positive 5 pi over 6. So that's going to land right here at negative 3 root 3 over 2 comma 1/2. So that's how you'll handle those negative rotations. Another thing, and I believe we did touch on this in Math 3, but we will need to review it, is converting between one unit to the other. So degrees to radians and radians to degrees. So just like when we convert units in other situations, we basically want to multiply by 1, but choose the values that work for what we want. So when I'm converting from degrees to radians, I want to introduce radians into my units and remove the degrees. So if I want to introduce radians, I'm going to multiply by pi divided by 180. And then it's the reciprocal for that. If I want to convert from radians to degrees, I want to introduce degrees into the unit measure. So I'm going to multiply by 180 over pi. And if you think about pi over 180 and 180 over pi, remember that's the same angle. It's the same angle size, just using different units. So 180 degrees is the same as pi radians. So we're really not changing the value. We're just introducing radians here by putting pi in the numerator and 180 in the denominator. And we're introducing degrees when I convert to degrees by putting 180 in the numerator and pi in the denominator. So I'm just going to do a couple of quick examples here. So when I convert 210 degrees, I'm converting to radians. So whatever I'm converting to, that's the one I want to be in the numerator. So that means I'm going to multiply by pi over 180 and then simplify as much as I can. So this would be 210 pi over 180. Now the degree over to the degrees cancel, and you're left with 210 pi radians over 180. I can also cancel by tens here. So we have 21 pi over 18. And both of those are divisible by 3 as well. So I can cancel out in the numerator. When I divide by 3, I get 7. And then in the denominator, I get 6. So this is the same as 7 pi over 6. So 210 degrees is 7 pi 6 radians. And we can see that on our unit circle as well. So we know that this is, switch to pencil. I know that this is 180 degrees. When I add 30 to 180, I get 210 degrees. So I know that's not a surprise to me, and I can see that that's exactly the same as 7 pi 6 radians. All right, so I will do this one and then move on. Negative 125. Now remember that negative rotations, I can also just think of that as a positive rotation. We repeat values on our unit circle every 360 degrees. So 0 degrees is the same as 360 degrees, is the same as 720 degrees. So I can take this negative 125 and just add 360 to that to make this a value that's between 0 and 360. So that's the same as 235. And I didn't have to do this. I could have just multiplied by pi over 180 right from the beginning. I just like working with positive degree measures. And then multiply this by pi over 180 degrees. So I'm introducing radians and I will cancel out the degrees. So 235 pi radians over 180, and then that will simplify, and you can just reduce this using your calculator. So 135 divided by 180 gives me the fraction 3/4. That's nice. So 3 pi over 4. And then this should make sense. So a rotation of 235 degrees should be 3 pi over 4. So here is, let's see, that's not right. I just realized I typed in the wrong calculator amount. So I typed in 135. 235 divided by 180. We get 47 pi over 36. Oops, very different. 47 pi over 36. So that's not going to be one that we'll be able to reference our unit circle. 47 36 radians. So if you ever get these negative values, feel free to add 360 or add 2 pi so you can get into that positive one. And then here to go the other direction, I'm converting from radians to degrees. That means I want degrees introduced into these units. So on A here, and I remember it helps also to remember I want to cancel out the pi. So I'm going to multiply that by 180 over pi. And then I'll get the degree measure that 2 pi thirds is equivalent to. So 2 times 180 is 360. The pi's cancel over 3, and we're left with 120. And that one we can see pretty easily. 2 pi thirds is right here. Whoop. 2 pi thirds is here. And remember, this is 90 degrees. Add 30 and I'm at 120. So that makes sense. So these should make sense if they're values that come directly from the unit circle. I'm going to move on and go on to the next page here. I think we've seen enough of this stuff for now. Okay. Okay, I am recording again. So on this, you turn the page and you will notice another blank unit circle. So I did this intentionally because of just how much practice it will take for you to feel confident in being able to do this on your own. So I left this up here. You are gonna want a quick reference to the unit circle without having to flip back and forth to the previous page. So I would either pause and fill this out again, or get that yellow one out with the larger one that I gave you in class, because you are gonna want a quick reference. Why do we use the unit circle? Why would I want you to be able to create the unit circle on your own? And that's because the unit circle is a quick reference tool to determine the sine, cosine, really any trig ratio for all of these unit circle values. So yes, there are degree and radian measures in between these points that we have, but these ones that we have, that remember we got from special right triangles, we got all of these ordered pairs from the special right triangles, are useful. This is just going to be a useful tool because we have exact values now. So when we, don't forget here, super, super important, x equals the cosine of theta, y equals the sine of theta. So when I say x and y, I specifically am referring to each of these x and y coordinates. So in other words, the cosine of pi halves the trig ratio cosine of pi halves. Instead of drawing a right triangle, getting the information we need, I can just reference this. The cosine of pi halves is 0. The sine of pi halves is 1. So same with all of these. 7 pi over 6, the cosine is negative root 3 over 2, and so on and so forth. So we're going to practice applying that right here in example 4. So we'll start with A, the cosine of 5 pi over 6. Cosine, I should be thinking x coordinate. So 5 pi over 6. You'll go up to your unit circle, find 5 pi over 6. Here's the rotation of 5 pi over 6. The cosine of 5 pi over 6 is the x coordinate there, negative root 3 over 2. And that's it. That's why we have the unit circle. It is a quick reference tool for figuring out these trig ratios. Sine of 3 pi over 4. So first I'm going to find 3 pi over 4 on my unit circle. Here's 3 pi over 4. The sine of that is the y value at that point, root 2 over 2. Now, tangent of 2 pi thirds. We only have sine and cosine on here, but don't forget that the tangent of an angle is the ratio of its sine divided by its cosine. We saw that on the first page. So if I can find sine and cosine of 2 pi thirds, then I'm just a step away from finding the tangent. So first I'm going to find 2 pi thirds. So here's 2 pi thirds. I have the cosine comma sine. The tangent is the ratio of sine of 2 pi thirds over the cosine of 2 pi thirds. Okay, so let's get that. Sine of 2 pi thirds is root 3 over 2. So the square root of 3 over 2 divided by, so I've got my numerator, root 3 over 2, the cosine, negative 1/2. Now I have a fraction and I'm dividing by a fraction. So I know that I can rewrite that by doing the numerator and then just multiply by the reciprocal. So my 2's cancel and I'm left with negative root 3 divided by negative 1, which is just negative root 3. So that's it with tangent. If you're using tangent, just remember that ratio and you'll have to do division, simplify, and then you're done. I'm going to skip a couple of these. Like this one's really straightforward. I do want to go down here and talk about D because 11 pi over 4 is not on our unit circle. So if I go back up and look, I've got 1 pi over 4, 2 pi over 4, which is pi halves, 3 pi over 4, 4 pi over 4, 5 pi over 4. 11 pi over 4 isn't on it, but we will just continue counting. So if I know that I'm down here at 5, 6 pi over 4, 7 pi over 4, 8 pi over 4 gets me back here where I started. So, and you could have recognized, okay, 8 pi over 4 is going to land me back at 0. And then there's just 3 more pi over 4s to get to 11 pi over 4. So again, this was at 8 pi over 4. So 9, 10 pi over 4, 11, right here. So what we see is that 11 pi over 4 is the same as 3 pi over 4. So 11 pi over 4, that is the same as the cosine of 3 pi over 4. So this isn't meant to trick you. It's just meant to get you to see that we start over at 2 pi or 8 pi fourths or whatever. So you can still continue counting to those values. So, and I was asked to find cosine. So that's negative root 2 over 2. Let's do another tangent. So 3 pi halves. 3 pi halves, if I want the tangent of that, what I really want is the ratio of the sine of 3 pi halves to the cosine of 3 pi halves. All right, so let's go to 3 pi halves. My sine, the y value, is 1, divided by the cosine, the x value, is 0. This is a problem because I cannot divide by 0. So what this means is that the tangent of 3 pi over 2 is undefined because we can't divide by 0. I'll skip this and I'll do another sine of negative pi thirds. So negative pi thirds, again, with those negative rotations, my advice is to first determine the positive rotation. So look where positive pi thirds is. and I'm going to go that same distance or that same angle amount in the opposite direction. So instead of going up here to positive 1 pi over 3, negative pi thirds is right here, which happens to be equivalent, exactly the same as 5 pi over thirds. So the sign of negative pi over 3 is the same as the sign of 5 pi over 3. A negative rotation of 5 pi thirds or of pi thirds is the same as a positive rotation of 5 pi thirds. And then I can just get that sign value, which is negative root 3 over 2. So that is how you use the unit circle. So you should be able to identify sine, cosine, and tangent of any of these radian amounts around the unit circle. We're going to move on to the Pythagorean identity. This is a super useful identity. I'm going to write it down and then prove it to you or explain it to you. So the Pythagorean identity states that for all values of theta, the cosine squared of theta plus the sine squared of theta always equals 1. So, and I'm going to build this and explain why that happens to be the case here in just a second. Okay, so here's a unit circle down here. Let me zoom in, focus on just this one little piece of paper. If I formed a triangle right there, this has XY coordinates. If I build a right triangle just by going straight down right here, remember that X coordinate from here to here is the cosine of theta. And this Y coordinate is the sine of theta. So I haven't introduced anything new. I'm just re-explaining that our X coordinate is the cosine, our Y coordinate is the sine of theta. Now I'm just going to draw a bigger version of this. So this is theta. We saw that this is the X value here is the cosine of theta, and that's me trying to label that. Okay, and that this right here is the sine of theta. All right, now remember I'm on the unit circle. So my hypotenuse has a value of 1. So this should start to come together in your brains now. This comes from the Pythagorean theorem, which we're familiar with in the sides of a right triangle, a squared plus b squared equals c squared, where a and b are the legs and c is the hypotenuse. So we're just applying that to right triangles formed from the unit circle. So a squared plus b squared would be cosine squared plus sine squared. So that's cosine squared theta plus sine squared theta equals 1. So I'm just applying the Pythagorean identity is an application of the Pythagorean theorem to any right triangle formed on the unit circle. So that's going to come in handy. When does that come in handy? Well, let's flip the page and we'll see an application of that. So when I look at this very next page, example 5 at the very top, it says use the Pythagorean identity. So let's just rewrite what that is because we're going to need it a lot. This is one you're going to need to have memorized. This is the Pythagorean identity, and given either the sine or cosine of an angle measure, that means we can automatically find the other one. So in example 5, we are told that the sine of theta is 0.8. Find all possible values for cosine of theta. So I know from my Pythagorean identity that sine squared plus cosine squared, or reversed, it doesn't matter what order you put them in, equals 1. My sine of theta is 0.8. So sine squared of theta is 0.8 squared. So I can just directly substitute that in. Now, 0.8 squared is 0.64. And I'm that much closer to solving for what the cosine of theta is. I want the possible values for cosine. So I'm trying to isolate cosine theta. So I'm going to subtract 0.64 from both sides. And I'm left with cosine squared theta equals 0.36. because I would do 1 minus 0.64. Now I have cosine theta equals 0.3, or cosine squared theta equals, and I just want my values for cosine theta. So I need to undo squaring, which is just taking the square root. And don't forget, here's why you were told to find all possible values, because when I take the square root of both sides, then I have to account for both the positive and negative root of the square root of 0.36, which is 0.6. So cosine theta may be positive 0.6 or cosine theta may be negative 0.6. We have two possible options there for that. I'm going to skip example 6. It's very similar, but I think there's two, maybe it is just one or possibly two examples on your homework like this. It's just applying that Pythagorean identity. So you're going to take the one you're given, plug it into the formula, and solve for the other one. So definitely come back to example 5 for similar homework problems like that. I want to jump down to reciprocal trig functions. Reciprocal trig functions, cosecant, secant, and cotangent, which sound overwhelming and confusing, but it's just the reciprocal of the 3 trig functions we already know, sine, cosine, and tangent. So the cosecant of theta, the symbols we use for that are the C, S, and C. So cosecant is just the full word, but the symbols are CSC for cosecant, and that is simply the reciprocal of the sine function. So 1 over sine theta. The secant function, which we just abbreviate with SEC, secant of theta, is just the reciprocal of the cosine function. So 1 over cosine function. And I don't know a good way to help you guys remember this or memorize this other than that the C and the S, they're always with the opposite one. So the reciprocal trig function for sine is cosecant, so it switches from S to C. And the reciprocal function for cosine from C is S. So secant, 1 over cosine, cosecant, 1 over sine. And you'll get practice with these, but that's just a helpful way to memorize it, in my opinion. Cotangent, that one's easy because the word tangent is actually in it. And the abbreviation for that is just COT. So the cotangent of an angle is the reciprocal 1 over tangent. Another way we could think of it, since we know that the tangent of theta is the ratio of sine over cosine, then I also know that the cotangent, or 1 over tangent, is just going to be the reverse of that, which is cosine theta over sine theta. So that's cotangent. There. So when you're you can find not only can we find the 3 trig ratios of all of these rotations, sine, cosine, and tangent, now we are mixing in 3 more, so a total of 6 trig ratios. So I can look at this, for example, cosecant of 5 pi over 6. Well, cosecant is just the reciprocal of the sine function. So this is the same as 1 over the sine of 5 pi over 6. So I would then look at my unit circle, find 5 pi over 6. The sine of 5 pi over 6 is 1/2. So the cosecant, 1 divided by 1/2, is simply 2. So it's one extra step, these reciprocal functions. Identify which one it's the reciprocal of, find that value, and then divide 1 by it. So let's do another one, secant of 3 pi over 4. So again, secant, I look up here, that's 1 over cosine. So 1 over the cosine of 3 pi over 4. So I would go to my unit circle, find 3 pi over 4, which is right here. Secant is 1 over cosine. So here's cosine, negative root 2 over 2. So it's 1 divided by negative root 2 over 2. So this I need to simplify. So 1 divided by that is the same as 1 times 2 over negative root 2. So this is true, but we can't write that as our final answer because I need to rationalize the denominator. To do that, just like we already know, I'm going to multiply by, essentially multiplying by 1, but really by the square root of 2 over 2. So that's going to allow me to write my final answer as 2 times the square root of 2 over the square root of 2 times the square root of 2, which again just turns into 2, and that's negative. And now I actually have 2 divided by negative 2, so this actually simplifies to just the negative square root of 2. So you definitely need to be comfortable with complex fractions and rationalizing the denominator. Let's do one more. So let's do cotangent of 2 pi thirds. Remember, cotangent is 1 over tangent of 2 pi thirds, or we can think of it as the cosine divided by sine instead of sine divided by cosine, like the tangent function. So if I can just find the cosine divided by the sine and then simplify. So 2 pi thirds, that's my angle I'm interested in. So I'm going to look at my unit circle, go to 2 pi thirds, here's the cosine, and here's the sine. So cosine divided by sine, see if I can get both of these in the same, there we go. 2 pi thirds, cosine negative 1/2, sine negative root 3 over 2. Got a complex fraction here. So I'm going to multiply by the reciprocal. My 2's cancel, and I'm left with negative 1 over root 3. Again, a root in the denominator, I need to simplify it by multiplying by root 3 over root 3. And then I end up with negative root 3 divided by 3. So these reciprocal functions, you may need to revisit these sometimes coming back to the definition. If you can remember, cosecant 1 over sine, secant 1 over cosine. The more you practice these, the more that you'll have those memorized. I'm not going to do these. It's just repeating the same concept. So I'm sorry that this video was longer than typical. I just wanted to get you guys through this section of notes. So please upload your notes to Schoology now so that I can make sure you've got them. And I will see you in class next time. Bye, guys.